Artemis II will be following a lunar free return trajectory, which is a class of Earth-Moon trajectories that allow a spacecraft to conduct a lunar flyby without the expenditure of any propellant after departing Earth orbit. Lunar free returns are typically divided into 3 phases with 2 maneuvers: translunar injection, outbound orbit, lunar flyby, return orbit, and Earth orbit insertion or Earth re-entry. We'll get into the full visualization of this orbit in a moment, but first it helps to view these orbits in a frame that rotates once a month so the Earth and the Moon appear stationary relative to each other. The spacecraft begins in a parking orbit around Earth. Then, at a phasing angle of about 125 degrees behind the Moon, it performs a translunar injection burn, raising its apogee to just slightly beyond lunar orbit. 5 days later, the spacecraft passes behind the Moon from Earth's perspective and begins the return orbit of the mission. The return orbit is a mirror image of the outbound trajectory and returns to Earth 5 days after the lunar flyby, at which point the spacecraft can either aerobrake back into Earth orbit or re-enter the atmosphere for a landing. A few important features about free return trajectories. First, we call them free because they don't require the expenditure of any propellant in order to return to Earth. But this is slightly misleading since it implies that the spacecraft wouldn't have returned to Earth if the lunar flyby hadn't happened, and that's not true. The translunar injection burn for a free return is only about 3.1 kilometers per second, which is slightly under the 3.18 kilometers per second required to escape from a 400 kilometer low Earth orbit. So even without the lunar flyby, the spacecraft would have returned to Earth anyway. We can see this by simulating the same TLI burn, but at the wrong time, so the spacecraft misses the Moon entirely. The vehicle departs Earth, travels out beyond lunar orbit, and then falls back to the Earth. But notice the time of flight. Without the lunar flyby, the flight took 14 days instead of the free return's 10 days. So in a sense, the return was already free. What the lunar flyby got us was a free reduction in time of flight, which makes the mission easier to fly. Second, this type of orbit is impossible to accurately describe with classical Keplerian orbits, but it can actually be well approximated by them. The orbit is well approximated by 2 elliptical orbits. The only complicated part takes place when the spacecraft is near the Moon. Even though this portion looks complicated in this frame, it's actually well approximated as a simple hyperbolic orbit in the lunar frame. Approximating a lunar free return as 2 Earth-centered elliptical orbits, tied together by a Moon-centered hyperbolic orbit, is what we call the patched conic approximation, and it's actually a good enough approximation for most preliminary mission design. Finally, in order to fly the correct free return, the vehicle has to fly by the Moon at an altitude of 3 to 4 lunar radii, about 6,000 kilometers. So if the goal is to land on the Moon, a free return trajectory won't work. A maneuver would have to be performed earlier in the flight to take the spacecraft off a free return trajectory and onto a different trajectory that'll take it closer to the Moon, where it can then break into a low lunar orbit and land. The previous flight that came the closest to flying a fully free return trajectory was Apollo 13, which flew by the Moon in April of 1970. The Apollo 13 trajectory wasn't a fully free return mission, however. When the explosion occurred, the spacecraft had already maneuvered off of a free return trajectory in preparation for breaking into lunar orbit a day later. Just 5 hours after the explosion, the crew had to maneuver back onto a free return trajectory in order to get home as quick as possible. Since Artemis II is not landing on the Moon and will not be breaking into lunar orbit, Artemis II will be the first example of a fully free return trajectory flown by a crewed vehicle.